All right, so today we're looking at 9.2. So we'll go ahead and go through these. We're looking at the first half of it, I should say. We'll go ahead and go through these notes, and then we'll look at some equations for you guys to do on your own, or some examples, I should say. So it says, if f and g are continuous on t on the interval I, then the equations x equals f of t and y equals g of t are called parametric equations. So this is kind of going to be a branch off of what we were doing in conic sections last section. And t is called the parameter. So essentially what it is it's defining x as in a new variable t and y in a new variable t. It says the set of points x comma y is obtained as t varies over the interval I, and it's called the graph of the parametric equation. So taken together, the parametric equations and the graph are called a plane curve denoted by c. So we're going to use c to talk about this plane curve. So we'll get into some examples in a minute, so you can just copy those down first. It says, when sketching by hand a curve represented by a set of parametric equations, you can plot the points in the xy plane, and each set of coordinates x comma y is determined from a value chosen for the parameter t. So you can choose different values for t, plug them into the equation for x, plug them into the equation for y to figure out what your x and y values should be. By plotting the resulting points in the order of increasing values of t, the curve is sketched out in a specific direction called the orientation of the curve. So that's what the arrows are for. It helps us figure out what direction they go in, and that's called the orientation. So looking at this example, it says sketch the curve described by the parametric equations x equals t minus 3 and y equals t squared plus 1 from -1 to 3. So what I would do if I were you guys is, since this piece you can just kind of make a little t chart. In this case we need 3 levels since we have a t, an x, and a y to look at. So I would just take the different numbers from -1 to 3. So I would take whole numbers from -1 to 3. So I listed them all up here. -1. Here, I'll try to point it out for you guys a little bit. So here we have -1. Here we have 0. Here we have 1. Here we have 2. And here we have 3. So those are all the whole numbers in between -1 and 3. So I take -1 and I plug it into the x function. So here I'm going to plug in -1. So -1 minus 3 gives me -4, and that's how I got that -4. Then I'm going to do it with 0. So I plug in 0 here. 0 minus 3, that's -3. I plug it in there. Then I do it with 1. 1 minus 3 is -2. 2 minus 3 is -1. And 3 minus 3 is 0. Then I do the same thing and I take the t values and I plug them into the y function. So I take -1 and I plug it in over here. -1 squared is 1 plus 1 is 2. That's how I got this 2. If I plug in 0, 0 squared is 0, plus 1 is 1. That's how I got 1. If I plug in 1, I get 1 plus 1 is 2. If I plug in 2, I get 2 squared is 4, plus 1 is 5. And if I plug in 3, I get 3 squared is 9, plus 1 is 10. So that's how I got these. Then, these are like coordinates. So this is a coordinate pair, x comma y, x comma y, x comma y, x comma y, and x comma y. So I just plot those points. -4, 2, that's over here. So I'm going to plot -4, comma 2, and that's this point here. Then I plot -3, 1, which is right here. Then I plot -2, 2, which is right here. And then -1, 5, which is right here. And then 0, comma 10, which is way up here. And when you connect them, you can draw a line to connect them. And then I know that the arrows go in this order, pushing to the right, because that's the order that the t values went in. So the first t value at -4, 2 was the first one, and then it progressed to the right as we got closer to 0, comma 10. So that's how I got this graph from that. So that's doing it by just kind of plotting the points, the x and the y points. You can also eliminate the parameters, so you can get rid of t altogether, and here's how you do it. It says eliminating the parameter is the process of finding a rectangular equation, and remember that a rectangular equation is any equation that has just x's and y's. It doesn't have the parameter t in there. So finding a rectangular equation that represents the graph of a set of parametric equations. And here's the process used to eliminate the parameter. So number 1, given the parametric equations, the first thing you do is you solve for t in one of the equations. Then you substitute that new value into the second equation, so it should be t in terms of x or t in terms of y. And then you will have a rectangular equation. So, the last part of the notes before we get into some examples. When converting equations from parametric to rectangular form, you need to understand that the range in x and y implied by the parametric equation may be altered by the change to rectangular form. So essentially, whatever bounds there were on x, whatever the numbers were that were given by x. So for example, in that example we just did, it was from -1 to 3. That can be changed or that can be altered when you change it to rectangular form. So in such instances, the domain of the rectangular equation must be adjusted so that its graph matches the graph of the parametric equations. So you have to adjust the domain to fit whatever the parametric equation would have been. Just a little hint for trigonometric functions: to eliminate the parameter in equations involving trig functions, always use the identity, or make use of the identity, sine squared theta plus cosine squared theta equals 1, which is one of those Pythagorean identities. So let's get into some examples. So we're going to look in your book. So go ahead and turn your book to page 653. So looking at 653, that first example up at the top is exactly like the one that we did in here in our notes. So I'm actually going to let you guys try that one on your own. So go ahead and pause the video and try example number 1. You'll see that it's a lot like the one we just did in our notes. And then when you're done, we're going to look at example number 2 on page 654. So let's come back together there. Alright, so what we're going to do here is we're going to eliminate the parameters. So essentially we're going to get rid of t altogether and just have a rectangular equation in variables x and y. So it looks like this one is going to be simpler to eliminate the t, or to solve for t I should say, because look at this one, it has 2 t's, so it might make it a little bit more difficult to do that. So in this first one over here, I'm going to multiply, or actually I'm going to square both sides. So if I square both sides, it should get rid of that squared on the bottom down there. So I'm going to get x squared equals 1 over t plus 1. Then if I multiply t plus 1 to both sides, I get x squared times t plus 1 equals 1. And I want to solve for t by itself, remember. So I'm trying to get t plus 1 by itself, so I'm going to divide both sides by x squared. So I have t plus 1 equals 1 over x squared. And last but not least, t equals 1 over x squared minus 1. So if you want to convert that into one fraction just to make your life easier, you get 1 minus x squared over x squared. So I'm going to take that and I'm going to plug it in to the y function wherever I see a t. So I'm going to plug it in there and there. So I'm going to get y equals 1 minus x squared over x squared. That's for the top t. And then on the bottom, I have another t. So 1 minus x squared over x squared plus 1. So that's t over t plus 1 essentially. So if I want to get rid of that x squared on the bottom, I can just multiply everything by x squared on top and multiply everything by x squared on the bottom, and it'll eliminate that complex fraction. So this would give me 1 minus x squared over 1 minus x squared plus x squared. So if I add on the bottom, I get 1 minus x squared over 1, which is just 1 minus x squared. So my new rectangular equation is y equals 1 minus x squared. So I can actually graph that pretty easily. That's just a parabola facing down that's shifted up 1. So the 1 shifts it up, and the negative makes it face down. So if I can erase some of this stuff to graph it. Let me not do that. Let me erase this. There we go. If I can pull up a piece of graph paper. Alright, so essentially, if I can draw my lines here, I have an x-axis right here. It's not very straight, is it? There we go. A y-axis right here. And I have my x-axis right here. Forgive me for not making them very straight. It's up 1, and then the downward parabola faces this way. So it looks something like that. Now you do need to be careful because at the top we did have this t is greater than -1 thing. So we need to understand that there is a direction. Well, the direction doesn't really matter when you convert it into rectangular coordinates. However, the domain of this function might be altered because of this t greater than -1 piece. So the way to figure out exactly what it is that you're looking at is I would just pull in or plug in a few values of t. So obviously if you plug in -1 to both of these, you're going to get 0 on the bottom of both of these fractions, and we can't have that. So I might plug in 2 as my first coordinate. Or actually imagine what it would be if you plugged in a number really close to -1, so the limit as it's approaching -1. So a number really, really, really close to -1, well, rewind. We'll get there in a second. Let's plug in negative 2. So if I plug in t equals negative 2, for x, if I plug in negative 2 on the bottom, that's going to be negative 2 plus 1 is negative 1, and the square root of that doesn't work. So actually, it says t is greater than negative 1, doesn't it? So obviously, I couldn't choose negative 2. Let me choose 0. If I choose 0, I get 1 over the square root of 1, which is 1. And if I plug it into the y equation, I get 0 over 1, which is 0. So I know that it goes through the point 1 comma 0, which is right here. So I need to figure out, as it gets closer and closer to negative 1, what would it go through? You can start plugging these in a calculator if you want to, but essentially if you get close, so the limit as x approaches negative 1 is going to put you at the point 0 comma 1. If you look in a calculator, you'll notice that the x value will go to 0 and that the y value will go to 1 as you get closer and closer to negative 1. And I'll let you guys put that in a calculator to figure that out. So essentially it's getting really close to this point, and it exists everywhere greater than that, so everywhere over here, which means that this piece of the graph is not part of my domain, so I need to erase that piece of the graph. So my equation is essentially y equals 1 minus x squared, and I can graph it right there. But the domain insists that x must be greater than or equal to 0. Or actually, sorry, not equal to, just greater than 0, because it can't actually equal that t value. So that's how I know that it's just this half of the graph, not the entire thing. All right, let's look at example 3. All right, so here's example 3 on page 655. Remember that this is a trig function, so in the notes we said that when you have trig functions, make use of the identity sine squared plus cosine squared equals 1. So I'm actually going to solve both of these for sine and cosine. So in this one, cosine of theta would equal x over 3, and in this one, sine of theta would equal y over 4. So if I make use of sine squared plus cosine squared equals 1, that means I have y over 4 squared, that's, oops, maybe make that look like a 4 more. Y over 4 squared, that's sine squared, plus cosine squared would be x over 3 squared equals 1. So if I simplify these a little bit, I get y squared over 16 plus x squared over 9 equals 1. Well, hopefully I should say, you recognize that this looks a lot like an ellipse, the equation for an ellipse. So we can actually graph it like we would graph an ellipse. So if I can pull up some graph paper, let me erase some of this stuff. So this ellipse is centered at 0, 0 because the x and the y have nothing being added to them. I know that on the y-axis it goes to plus or minus 4 because the 16 is under the y and the square root of 16 is 4. So it goes to up to 1, 2, 3, 4. That's the vertice up there at 4. And it goes down to 1, 2, 3, 4. That's the vertice down there at 4. For the 9, the square root of 9 is 3, and that's under the x, so I know it goes out on the x-axis 3 this way, and I know it goes out on the x-axis 3 this way. And again, that's because it's centered at that point. If you connect these points, it looks something like this, the best ellipse you can draw. So that's what the graph looks like. The only other thing we're concerned about now is the direction that we're looking at. And you can check the direction by plugging in, I know I erased the equations up there at the top, but you can plug in the different values for theta to check where it starts and like where it's going to. So essentially, if you plug in 0 for theta, and you can look back at those equations we already wrote down. If you plug in 0 for theta, which is the first number in the domain, you get 3 cosine of 0. Well, cosine of 0 is equal to 1, so that's just 3. And if you plug it into the y equation, 4 sine of 0 would be 4 times 0, so that's 0. If I plug in pi over 2 to theta, I have 3 times cosine of pi over 2 for x, which is cosine of pi over 2 is 0, so this one's 0. And for y, I have 4 times sine of pi over 2, which is 4 times 1, which is 4. And if I plug in 4, or pi, if I plug it into the x, I get 0 again. I get 3 again, because cosine is equal to negative 1. Negative 3, my bad. And if I plug it into the y equation, I get 0 again. So if I look at these 3 points, 3, 0 is right here. 0, comma 4 is up here, and negative 3, 0 is right here. So if I'm looking in order of the way that it's going this way. So the direction is going counterclockwise, and you can draw little arrows pointing that way so that everybody knows which direction it's going. All right, so that's the first half of 9.2, 9.2a. We're going to look at the next half tomorrow, finding parametric equations, but that's it for today.